Oi, TensorLLM, tensorizing multi-head attention for enhanced reasoning and compression in LLMs. Cool thing for you today, if you're the laser paper from like a year and a half ago or something, it's a similar deal here, is they are effectively forcing different attention heads to all work within the same subspace and hoping to get reasoning gains accordingly. There's a few different potential avenues that future work could take this one, but I thought it was interesting, and I say we just get straight into it. Before we start, remember to like, subscribe, comment, share, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, support me either through Patreon or YouTube. For as low as $1 per month, you can get early access to my videos, or for a one-time payment, hit my Venmo. And if you'd like to borrow my brain for an hour or two, book a consultation call. All links are over on my Linktree. Let's get started. Disclaimer. So, some prior work has related to this kind of thing. Of note is a paper that I covered probably a year ago or something called Laser, in which they did singular value decomposition on the actual weight matrices of the MLP in the actual transformer, meaning that they can take a weight matrix, split it up into a decomposition SVD that is effectively just three matrices where they now have control over how granular the actual representations are. They can lower the actual rank by removing columns and rows from each of the three matrices and then combine it back together again. And they found that the lower rank parts, aka the kind of subspaces that the weights were acting in, that were less, not quite as big, lower magnitude, less importance, were actually pretty noisy and hurting model performance, whereas it was only the high rank actual components that actually mattered and contributed to actual performance. I need to stop saying actual, geez. Anyways, it was kind of cool, didn't really get used. It was a kind of finicky method to do some minor performance improvements across just factuality, which is whatever, right? But it was cool. It did demonstrate that these overparameterized models can probably be pruned in an intelligent way and set up in a more intelligent way in the future if we can find a better way to go about things. And in this paper, something similar is going to happen. Prior works that tried to do this with the actual attention mechanism, that tried to actually do this in the attention level, didn't really work. They were not effective, partially because they seem to not leverage domain knowledge, which is a weird way to phrase that. The way I prefer they phrased it is basically that you need to look at all heads in total, all attention heads combined, because superposition and all, they are not working entirely independently. They probably do things together that matter together. And so this paper's one of its big innovations is to say, okay, let's actually do our tensor decomposition, but with all the heads at once, right? And this is important because heads in the same layer tend to focus on the same information and do the same kind of stuff. So if you just were to decompose or break apart or edit a couple of the heads or all of them independently, then you're going to probably break things. Now, these authors conjecture that the weights of multi-head attention in a single transformer layer contain reasonably related information in a subspace which is shared across multiple attention heads. Immediately, light should be going off, bells going off, whatever you call it, whatever the phrase is, about multi-latent attention from DeepSeek, right? This idea that we actually have a single subspace being worked on by all attention heads, as opposed to each attention head working in its own subspace, right? Which is possible, don't get me wrong, like go read some old anthropic interpretability papers, and yes, we can talk about like each head reading and writing from the actual digital stream and everything independently, but in reality, right, it's often useful to do these things combined and together. So the question is, can we enforce using an actual shared subspace among all of the actual heads? And would that help performance? Now, if you're already aware of singular value decomposition, but you haven't heard of Tucker decomposition, it's just the higher dimensional tensor version of what Tucker is. So same shtick, but like more generalized, basically. You end up with a core tensor and then a bunch of matrices, but same thing fundamentally is happening there. What we're going to do is we're going to take the weights in your attention mechanism, your MHA, and we're going to concatenate them together into a set of 3D tensors, where each attention head is now a 3D tensor, and then apply that Tucker decomposition and force a common set of factor matrices across these decompositions, aka force the same actual subspace to be used across heads. So the weights themselves in the attention heads will be forced to work within a shared subspace. Now, of course, you don't actually want to necessarily store the tensor weights in 3D or anything. We usually store them in 2D because that's actually faster to compute. Matmuls are fast, of course. So we're going to fold these weights up. If you take our query key value and output projection weights, which are each of size model dim by number of heads times head dimension, we split them up by head dimension to get for the ith head, right? To get individual matrices of size model dim by head dim for each head. And then we create a new tensor that is just the query key value and output stacked on top of each other for a single head. So all weights related to a given head, all weights related to a specific head, get all of those weights combined into one tensor. Do this for all h heads, and then stack all of those together along this new head dimension to get a 4-dimensional tensor of shape model embedding dimension by head dimension by 4 being query key value output, right? And then by number of heads. Then we do Tucker decomposition on that 4D tensor. And once we have our Tucker decomposition, the denoising process is just grabbing the better ranks and leaving the smaller ranks out to dry. And they supposedly get results that involve significantly improved reasoning abilities. We can see here on 4 different benchmarks, chosen kind of oddly in my opinion, but whatever, and 3 different models, Roberta, GPT-J, and Llama 2. Pretty consistently, you see higher accuracy scores, occasionally lower loss scores on their new Tucker decompositioned version, right? As well as this third metric along all of these is the actual compression rates compared to the original model's weights, as low as 12% compression and as high as 75 or actually 250% or times compression, I guess. They also went back at that laser method that works in the MLP layers, and they said, is it helpful to do both laser and our own thing? Which one's better? Can we combine them? Of course, they are, one does attention, one does MLP, so you can combine them. It just doesn't make any sense to combine. Is it actually worth it? Case 1 is traditional laser on the MLP. Case 2 is doing laser on both the MLP and the attention layers. And again, laser being different because it just does matrix-wise decomposition as opposed to actual tensor-wise and like this forcing the same subspace. And then case 3 was the new method introduced in this paper plus laser on the feed-forward layers. And with that, similar deal, all but one of the models and benchmarks combination didn't have the case 3 winning for accuracy. Now, I'm not fully clear on how this whole thing works. I've not bothered to do a Tucker decomposition from scratch or anything. I just took the intuition of, oh, it's SVD but tensors. Cool, good enough for me. And my question would be, instead of decomposition post hoc, can we train a model from scratch with those tensor shapes? Like actually defining our parameters in terms of those Tucker matrices in the tensor, and then have those be our actual parameters we train. And so from scratch, forcing the model to actually keep the MHA within a shared subspace, so like all heads in the actual attention mechanism in a shared subspace. Does that work? I believe, I could be wrong, I believe it would require more parameters because I think this is true of SVD, is that if you wanted to just like train in an SVD format of an actual weight matrix, what you have is like way more actual entries in your 3 matrices now, and that would be less than ideal. That's my impression. So it would have to be a pretty big performance increase to be worth it if I'm correct on that, but don't quote me on that. I could be wrong. And they do have the issue of, it seems like for different data sets and architectures, the hyperparameters are not absurdly clear. It doesn't, the screen always use hyperparameters or anything. It seems like you do have to tune them pretty extensively to get things to work well, which is definitely an actual implementation issue. But anyways, those are my thoughts for y'all today. Hope y'all enjoyed. End of video. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below. For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.